Next, we're going to talk about what it means for a function to be continuous. So definition, f of x is continuous at a, so a point A in the domain. F of x is continuous at a if the limit of f of x as x approaches a equals f of a, and we're going to take infinity out of consideration for when a function is continuous, so the limit will not be infinity and the function will not go off to infinity at that point A. And remember, we can check whether a limit exists by checking what happens on both sides of the limit. So if we want to check for continuity, what we need to show is that the limit as x approaches a of f of x equals f of a. But to do that, we can check the limit on the right and check the limit on the left, and if they're the same and they equal f of a, then this equation will be satisfied. So right there, in this remark, this string of equalities, there are a couple places where that can go wrong. And before discussing continuity, we're going to discuss possible discontinuities, places where this string of equations could go wrong. And to illustrate them, we'll look at this graph. Let's call it f of x. So we have this function. It goes up here, open dot, close dot, open dot. And then we have a vertical asymptote at 7. And then after 7, it actually doesn't matter what it does, so we'll just say it looks like that. Now, there are 3 discontinuities. And we could check these, well, we will eventually check these discontinuities with these limits. But there's a convenient graphical understanding for when a function is continuous. The limit will equal the function at a point if, as you travel through that point, you can draw the graph without lifting your writing implement. So if the limit on the left equals the limit on the right, and the function equals that at that point, then as you travel through that point, you can draw the function without lifting your writing implement. And with that understanding, we see that there are 3 different discontinuities here. One here at 3, one there at 5, and then one at 7. So this function is not continuous at x equals 3, 5, and 7. I'll just write it like that because I'm out of room on the side of the board. So this function is not continuous at 3, 5, and 7. But let's look at, so that was just from the, you can't go through the function at 3 without lifting your writing implement, at 5, and at 7. But let's see where this limit equation goes wrong. So let's say at x equals 3, let's do this in bullets. At x equals 3, what happens? Why is it not continuous? Well, the limit, I should put a value down here. Let's make it -2 down there. At 3, the limit as x approaches 3 from the left is 4. And the limit as x approaches 3 from the right is -2. So at x equals 3, limit as x approaches 3 from the left of f of x. Well, which one did I write for? I wrote right first over there. So I'll say right first down here. Limit as x approaches 3 from the right of f of x does not equal limit as x approaches 3 from the left of f of x. From the right, the limit is -2. From the left, the limit is 4. But in this bullet point explanation, I'm not going to say those specific values. Just the fact that this first equal sign is not true at x equals 3. Next, at x equals 5, I'm going to leave a line to write something under this bullet point. So if you're taking notes, you might want to also leave a line there. At x equals 5, what happens? Well, the limit as x approaches 5 from the left equals 2. The limit as x approaches 5 from the right is also 2. But f of 5 is 6. So the limit equals 2, but the function f5 equals 6. So at x equals 5, limit as x approaches 5 of f of x does not equal f of 5. Maybe I will just write the numbers with the other color. So maybe I'll just write them up here. From the right we have -2 up there, and from the left we have 4. Limit as x approaches 5 is 2, and 2 does not, oh, I'm not going to have room. Here's what I'll do. I'll write this one smaller. So here, the limit as x approaches 5 is 2, and f of 5 equals 6. And they're not equal. Now what happens at 7? Well, at x equals 7, maybe I should say when x equals 7. At x equals 7, what happens? Well, the limit on the left and the limit on the right are both infinity. Oh. How didn't I notice this? I believe I did say not equal when I said this. That should say not equal to positive or negative infinity. And I definitely said not equal to. I said we restrict positive, negative infinity from this. So that definition should say not equal infinity. Here, f of 7 is not infinity. That's f is not defined at 7. But the limit as x approaches 7 from the right and from the left are both positive infinity here. So we'll just say at x equals 7, limit as x approaches 7 from the left equals positive infinity. We actually don't even need this piece over here, so I'm just going to get rid of it. And the fact that on the other side we get infinity doesn't add to it. So the fact that one of the sides we get a limit of infinity, that's enough to throw off this equation. So right here we have 3 different types of discontinuities. These are the 3 different discontinuities, and we have we have words that can describe both of them. So here we call the discontinuity which one do we have here? So it goes, the function is up here and then it jumps down there. We call that a jump discontinuity. So a jump discontinuity. The next one, at x equals 5, when it's not continuous because of a single point, we call that a removable discontinuity. A removable discontinuity. And the reason we call it removable is because we can remove the discontinuity by changing what happens at one point. Up here, to remove the discontinuity, we'd have to change what happens at a lot of points. And down here, when we have a vertical asymptote, we call this an infinite discontinuity. So we have 3 different discontinuities. That says and. We have 3 different discontinuities, and we can describe them with limits. We can also describe them with a graph. So a lot of the functions we will deal with are continuous, at least on their domains. So let's make another definition. Our first definition was what it meant for a function to be continuous at a point. But here, this next definition just tells us what it means for a function to be continuous. So remember, a function was continuous at a point if the limit as x approached that point of the function was the function evaluated at that point. Here we have a function f of x is continuous if f of x is continuous at all points in its domain. So we take the domain, if f of x is continuous at all of those points, then we say we have a continuous function. And we have these two theorems on continuous functions. Most of the functions we'll be seeing are continuous functions, at least on their domains. So this first theorem says that polynomials, rational functions, root functions, trig functions, inverse trig functions, logarithmic functions, and exponential functions are all continuous on their domains. So these functions will have points. Some of these functions will have x values at which they're not continuous, but they are still continuous functions because we are restricted to just the points in its domain. And all of these are continuous on their domains. We also have this next theorem, which tells us if we add, multiply, or divide continuous functions, then we're still going to get continuous functions. So here, if f and g are continuous at a point A, and c is a constant, then f plus g, f minus g, f times g, f divided by g, and a constant times f are all continuous at A. So let's look at applying these two theorems with these four examples. So here we have the first one, x plus 1 over x minus 5, a rational function. We want to find the interval on which it's continuous. Maybe I should throw directions on here. Find the interval on which each function is continuous. C-O-N-T, continuous is a pretty long word. So first, we have this rational function, x plus 1 over x plus 5. Well, what's the domain of a rational function? The domain of a rational function is everywhere except where the denominator is 0. The denominator is 0 at 5. So it's continuous everywhere else. It's continuous on its domain. Next, square root of 16 minus x squared. I'm going to need to do a little side work here for this one. We need the domain of this function. Well, remember, the domain of a square root function will be wherever what's under the square root is positive or 0. So set the inside of the square root greater than or equal to 0. We get x squared is less than or equal to 16. And from that, we have x's between 4 and negative 4. So the interval on which it's continuous is negative 4 to 4. Yeah, okay, negative 4 to 4. Did I spell that right? Yeah, okay. Next, x to the 7th minus 4x to the 6th plus 3x. Well, this is just a polynomial. This is continuous on its domain. A polynomial's domain is everything. Negative infinity to infinity. And what about this last one? X to the 7th minus 4x to the 6th, and instead of 3x, we have plus 3 over x. What is the domain of this function? Well, instinctively, you might say the domain is everything but 0, because the only bad point here is where this denominator is 0. And that is correct. But what if we had to explain why this function is continuous on its domain? Well, oh, I erased the theorem. Well, that's okay. You probably have it written down, or you could be warned. Let's look at these two pieces of this function. Right here, we have a polynomial. That's a polynomial. Right here, 3 over x, it's a polynomial over a polynomial. So that's a rational function. So right here, we have the sum of two continuous functions on their domains. So we have a polynomial and a rational function, which are both continuous on their domain. So this entire function is continuous on its domain because of the first result here that was erased. Because the sum of two continuous functions is continuous. But all of this boils down to these functions are all continuous on their domains. There are, just like with limits on the left, limits on the right, there are notions of continuity from the right, continuity from the left. I'm not too concerned with that. I mean, it's more tedious than necessary, especially if you cover limits from the left and right as extensively as we did. So I'm not too concerned with that. But one thing I am concerned with is a question like this. Finding a value that forces the function to be continuous. And I need a well, let's actually do two examples. Let's make an observation with this example and then do an example. So example, f of x. So y is f of x equals this function, negative x squared plus 4 if x is less than or equal to 3, 4x minus 7 if x is greater than 3. Why is this function not continuous at x equals 3? So question 1, we'll be able to answer that down there. Question 2, find the value a which makes f of x continuous on negative infinity to infinity, and let's give a function. F of x equals 4x squared minus 7. F of x equals 2ax plus 3. And this is when x is less than or equal to negative 4. And this is if x is greater than negative 4. So let's do these two examples. So the first one, why is that function not continuous at x equals 3? Well, let's check. We have a function that's defined differently on the left than it is on the right. So let's check the limit on the left and the limit on the right and see if they're the same. So limit as x approaches 3 from the right of this function equals what? Well, this is the one that defines it on the right. Equals limit as x approaches 3 of 4x minus 7, which equals what? Well, we can just use the substitution, the algebraic limit laws. So substitute 3, you get 5. Okay? How about the limit on the left? Notice here the limit on the left is going to equal f at 3. So the limit on the left is what? What's the function? Negative x squared plus 4. So the function is defined as negative x squared plus 4 on the left of 3. And what happens here when we substitute 3? We get negative 9 plus 4, which equals negative 5. So right here we checked the limit on the left and the limit on the right. And this function is, let's actually answer the question, why is this function not continuous at 3? Since, this is a lot of words. So we'll say f is not continuous, C-O-N-T, at x equals 3, since, we did all the work, so I'll just say since 5 does not equal negative 5. If 5 did equal negative 5, then it would be continuous at 3. So you could see a question like that. You could also see a question like this. Find the value a which makes f of x continuous everywhere. So here we have another piecewise function. On the left of negative 4 and equal to negative 4, the function is 4x squared minus 7. On the right of negative 4, it's 2ax plus 3. A is a constant. So we want this function to be continuous. Well, what we're going to do, we have this function. It's something before negative 4, and it's something after negative 4. What we want to do is force those two things to be equal. So let's find the value a, which makes these two things equal at negative 4. So limit as x approaches negative 4 from the right, of our function equals the limit as x approaches negative 4 of which one is on the right? Right is greater than, so that's this bottom one. 2ax plus 3. And what does that equal when x equals negative 4? Negative 8a plus 3. And how about limit as x approaches negative 4 from the left? What is that? Well, the function on the left of negative 4 is that one. Well, it's defined as that, I should say. 4x squared minus 7. And what does this equal when x equals negative 4? 64 minus 7 equals 57. Well, okay. So right here we have limit on the right equals negative 8a plus 3. Limit on the left equals 57. So to force it to be continuous at negative 4, we need to set these equal and solve for a. Negative 8a plus 3 equals 57. Subtract 3. Negative 8a equals 54. Divide by negative 8. A equals 54 over 8. Take a 2 out of both of them. 27 over 4. And there's a negative sign. So once we get there, let's go back and make sure we answered the question that was being asked. This question says, find the value a which makes it continuous on negative infinity to positive infinity. Well, we claim that this works, but all we showed here was that this function is continuous at negative 4 when a equals negative 27 fourths. So we should really answer the question that's being asked. So we could say, since f of x is a polynomial on each side, we can be a little informal in this, on each side of negative 4, when a equals negative 27 over 4, f of x is continuous on negative infinity to infinity. So you could have explained that a little more, and I'm okay with an informal conclusion here. You could have said something like, well, it's a polynomial on negative infinity to negative 4, so it's continuous there. It's a polynomial on negative 4 to infinity, so it's continuous there. And then this makes it continuous at negative 4. But I'm okay with just saying something like that. I mean, yeah, I'm okay with that. But the observation is we have a polynomial over here. It's continuous on the one side of negative 4. We have a polynomial here. It's continuous on the other side of negative 4. And the computation we did here forces it to be continuous at 4. Now, there's one more result on continuity I'd like to cover. It's an important result, so I'm going to write it here. Well, that logic didn't quite follow. It's important, so I'm going to write it here. I could have written it anywhere. Well, anywhere on these boards. Theorem. The limits, we've computed many limits. There are still, right now, some limits we can't compute with the results we have. For example, limit as x approaches pi of sine of x. We can't compute that. Now, you might be able to set up a nice squeeze theorem argument, but we can't compute that yet. However, this theorem will help us compute that. If f of x is continuous at L and limit as x approaches a of g of x equals L, then conclusion, limit as x approaches a, I don't need parentheses there, of f of g of x. So here we have a composition, f of g of x. If it's a continuous function, then we can push the limit inside the outside composition. So we have the limit of a composition of functions then we can push the limit inside, and the limit of g of x is L, so this equals f of L. And let's just look at one example. One example here. Limit as x approaches pi over 2 of cosine of x minus pi over 4. So what does this equal? I'm probably going to wind up going on this board here. So what does this equal? Well, with this result, we can push the limit inside the cosine function. So cosine of the limit as x approaches pi over 2 of x minus pi over 4. So this theorem here allows us to push this limit inside the cosine function, and now we can use the limit laws on the inside. So cosine of pi over 2 minus pi over 4, which is cosine of pi over 4. What's the cosine of pi over 4? Pi over 4 is in quadrant 1. Cosine is adjacent over hypotenuse. There's our triangle. There's pi over 4. Adjacent is 1. Hypotenuse is root 2. Positive from that quadrant. So we get 1 over root 2. And notice that what this did is allow us to treat this limit essentially as a direct substitution. Continuous functions are very important. One important thing to keep in mind is a continuous function you can draw without, well, you can think of it as a function you can draw without lifting your writing implement. That type of reasoning will almost definitely show up either directly or indirectly on at least one of the tests. So you can keep that in mind, but also some of these computations we've done could show up on tests as well. And of course, all computations we've done could show up on tests.